Hello. We're moving into higher dimensions today. Um, Up until this point, we've been talking about uh, finding volumes under a surface, where we've written the surface as z is equal to f of xy, and we have this two-dimensional domain of integration. And what we've been able to do is we've been able to say, well, the volume under the surface uh, and above the xy plane can be calculated using a double integral over this domain of f of xy dA. We brought that into an understanding this integral of f of xy dA by taking this two-dimensional object and making it into a three-dimensional object. So things are going to get a little bit more complicated to think about and to visualize when we start talking about finding a triple integral over some three-dimensional region. So what we're talking about now, here again I like to think about this type of function here, f of x, y, z, as maybe keeping track of what the temperature is at every point in the room. Or another thing you could think about is, let's say you have uh, some object that has different density throughout. And your goal might be to find, well, how much total temperature is there in the room? Or how much total mass is there on an object? And when you're in that situation, then that's when you're going to do this triple integral. If we wanted to try to visualize this idea of a triple integral, right, what we're talking about is we're talking about this like blob, E, it's a three-dimensional blob, and now we need to go into the fourth dimension to talk about what the function value looks like. And that's just, we can't, it's really hard to do, it's really hard to think about, but maybe what we could do is we could color the different points in this object and say, okay, when you've got more darker colored objects, it's a higher value. When you have more lighter colored objects, it's a lighter value. It's just hard to visualize. So now let's talk about this idea of this triple integral. So just as before, so what we're trying to do is we're trying to calculate, trying to add up a whole bunch of little bits of things over now a three-dimensional object. So if we were trying to do like a Riemann sum, instead of it being these objects where you take the height times the little bit of d area, then now in this case the little bits are going to be little bits of volume, and then we multiply by the height. Okay, so here's our setup. Now, before we were taking double integrals over regions in the two-dimensional plane, the xy plane. Now we want to take integrals over three-dimensional regions, and those are going to live in the xyz plane. So the simplest type of region in three dimensions is the idea of a box. So let's say we have a box where there's some x goes from A to B. There's some y that goes from C to D. And then there's some z value, this height, that goes from what we're going to call it is R to S. If you deal with enough math problems, you start to see, like, you start to run out of letters, because we couldn't really say e to f because e is for an exponent, f is for a function. We use g and h for functions. We use I and j for indices, k for an index, m and n for dimensions. So you start to run out of letters. But what we're dealing with is we're dealing with this box. So these are the x coordinates, these are the y coordinates, these are the z coordinates. And what we're hoping to do is we're hoping to take an integral over this box B. Just like for rectangles, taking an integral over a box is a simple thing we can do. So what Fubini's theorem says is that we can take our function and we can integrate with respect to x, y, and z, but we can also integrate however we want, whichever order we want to integrate into. So what we're doing is we're doing this triple integral. We don't have to worry about the Riemann sums, at least for the types of integrals that we're going to do. And so you can just take the order of integration and you can rearrange it however you want. Whichever makes your life easier. Okay, so another thing you can say is if f of x, y, z is written as a product of a function of x, a function of y, and a function of z. So if f of x, y, z is equal to g of x times h of y times I of z, then this triple integral, so the integral of g of x, h of y, I of z, times dx, dy, dz, that is going to give us, we can break that integral apart and we can multiply it. So if this is on a box, we can write it as the integral from x goes to a to b of g of x dx, and then we can multiply it by the integral from y is equal to c to d of h of y dy, and the integral from z is equal to r to s of I of z dz. So this is especially going to be useful later on when we end up taking this Cartesian coordinates. So in our Cartesian coordinates, we have a little bit of volume is equal to dx times dy times dz. We're going to deal with regions that are better represented in polar-like three-dimensional coordinates. That'll be coming up soon. All right, so let's do a quick example of this. Let's say we had this triple integral over a box that looks like this. Well, let's do it first by iterated integrals, and then we'll do it more simply. So what we're seeing here is we have an integral from x goes from 0 to 1, y goes from -1 to 2, z goes from 0 to 3 of x, y, z squared, dz, dx, dy, dx. And so first integrate with respect to z. We get x goes from 0 to 1, y goes from -1 to 2, z squared becomes z cubed over 3, evaluated from z goes from 0 to 3, dy dx. 3 cubed is 27. Oops, I forgot my x and my y. Z cubed is 27, so what we get is 27 divided by 3 is 9, and so we get that that evaluates to 9xy dy dx. All right, we've done one integral. Now we iterate and we do the next integral. The integral from -1 to 2, so we have 9x, and then y becomes y squared over 2, evaluated from -1 to 2, and all that's inside that outer integral. The integral from -1 to, so evaluating from -1 to 2 gives us 4 minus 1 is 3. So we get the integral from 0 to 1 of 27 halves x dx. And then we do this one more time, integrate with respect to x. We get 27 over 2 x squared over 2 evaluated from 0 to 1, giving us 27 fourths. But like I was saying, this is now a function of g of x times a function h of y times a function I of z. And so because of that, we can integrate each of them individually. So this integral is actually equal to the integral from 0 to 1 of x dx times the integral from -1 to 2 of y dy times the integral from 0 to 3 of z squared dz. And that is probably easier, less chances to get into trouble and have trouble. So x squared over 2 from 0 to 1 times y squared over 2 from -1 to 2 times z cubed over 3 from 0 to 3. And you're really starting to see this is exactly the same calculations we did before. We get 1/2 times 4 minus 1 over 2 times 27 over 3, which gives us 27 fourths. Alright, so things get difficult when regions are not boxes, and that's the thing we're going to talk about next. And it also gets difficult when regions are best defined in polar-like coordinates. So that's coming, but right now we're going to talk about regions that are not boxes, but we'll save that for the next video. See you shortly.